All right, today we're going to pull back the curtain on a really clever search algorithm called Beam Search. It's a super powerful tool for finding a good enough answer, and fast, without getting totally lost in a sea of possibilities. So let's dive in and break down exactly how it works. So, picture this. You're standing at the entrance to a massive maze. How do you find the exit? I mean, checking every single path would take you forever, right? This is the exact problem that smart search algorithms are built to solve. They need a better way to navigate the chaos, and that's what we're here to figure out. Here's our game plan. First, we're going to look at the algorithm that kind of started it all, best first search. Then we'll see why its need for memory became a huge problem. That's when we'll introduce Beam Search as the solution. And finally, we'll get into the really interesting part, the trade-offs you make when you choose speed over guaranteed perfection.
Okay, so to really get a handle on Beam Search, we've got to start with its ancestor, best first search. You can think of it as the foundation that Beam Search was built upon.
So, let's say we're starting at point A, and we have three choices. Go to B, C, or D. Each one has a heuristic cost, which, by the way, is just a fancy way of saying an educated guess about which path is the best bet. Now, best first search is pretty greedy. It just looks at the options and picks the one that seems best right now. In this case, C has the lowest cost of 25. So boom, that's our next move.
The process itself is pretty straightforward. You start somewhere, you look at all your options, and then, and this is the key part, you add all of them to a sorted list in your memory, something called an open list. Then, you just pick the single best option from that entire list for your next step. The other choices, like B and D in our example, just hang out in the list, waiting to see if they ever become the most promising path later on.
And, well, that brings us to the fundamental flaw with this whole approach. You see, keeping every single unexplored option in memory starts to become a massive, massive issue.
This open list we talked about, it's a global list. And with every single step you take deeper into the search, more and more nodes get piled onto it. It just grows and grows relentlessly, eating up a huge amount of memory. This is what leads to something called exponential complexity. You see it written as OB to the power of D. So what does that actually mean? Well, B is how many choices you have at each step, and D is how deep you're searching. The scary part is, as D gets bigger, as you go deeper, the memory you need just explodes. It makes this whole method totally impractical for really complex problems. So, how do we fix this memory nightmare? Well, this is where Beam Search comes in, and honestly, it's a much more focused and frankly elegant solution. At its core, Beam Search is just a tweaked version of Best First Search, but it has one absolutely brilliant twist. Instead of keeping every single possible path in memory, it decides from the get-go to only keep a certain number of the very best options at each and every step.
And that certain number has a name. It's called the beam width, usually represented by the Greek letter beta. The best way to think about it is like a flashlight beam in a pitch-black room. Instead of trying to light up the whole room at once, you focus a narrow, powerful beam on just the most promising spots. The width of that beam, that's your beta.
All right, theory is great, but let's see how this thing actually works in practice. We'll go right back to our original example and apply this new rule. Okay, so we're back at node A. We've got the same three choices, B, C, and D. Nothing new there. But here's the game changer. We're now going to apply a constraint. Our beam width, our beta, is going to be 2. What that means is we are only allowed to keep the 2 best options, period. And here's the crucial part. We look at our 3 options and we find the best 2. That's C with a cost of 25 and B with a cost of 32. We keep them. But node D, with its higher cost of 35, it's outside our beam. So it gets pruned. And when I say pruned, I mean it is gone for good, completely discarded from memory forever. The source material we looked at put it perfectly. It said, you keep only the best 2 from all the choices. That is the simple point. It's a ruthless strategy, for sure, but it is fantastically effective.
Now, you know that this kind of ruthless efficiency has to come with a catch, right? So let's talk about the trade-offs. What do we gain by using Beam Search? And just as importantly, what might we lose?
This visual really says it all, doesn't it? On one hand, you have Best First Search, which is trying to juggle this constantly growing global list of every possibility. Then you have Beam Search, which has a nice, fixed, small memory footprint. It's a complete shift in thinking, from a global perspective to a strictly local one. You only care about the best options right now.
This table really lays out the whole trade-off. Let's just walk through it. First, look at space complexity. Best first is exponential, which we know is bad. Beam Search, on the other hand, is O to the B times beta, meaning its memory usage is fixed and predictable. That's a huge win. But, and this is a really big but, look at completeness. Best first search is complete, which means it guarantees it will find an answer if one exists. Beam search makes no such promise. Because it's so aggressive about pruning options, it might accidentally throw away the only winning path. And finally, notice that neither algorithm is optimal. Neither one guarantees finding the absolute best or shortest path, just a path. So, this lack of completeness, that's the real price we pay for all that speed and memory efficiency. The big question is it worth it? You know, the source material warns that by being so picky, beam search runs a very real risk. You could throw away a path that looks kind of bad right now, only to find out later that it was actually the only way to the goal. You might have already pruned the right path, and you'll never be able to get it back. And this leads to a fascinating little side note. What do you think happens if you make that beam as narrow as it can possibly be? You said beta equal to just 1. Well, you end up with an even simpler algorithm that only ever keeps the single best option. And that super greedy approach has its own name. It's called hill climbing.
And that really brings us to the heart of it all. You know, in huge fields like AI language translation or speech recognition, exploring every single possibility is just impossible. Beam search is so powerful because it finds a very good translation or a very good transcription, and it does it quickly. It trades that ironclad guarantee of perfection for practical speed and efficiency, which leaves us with a bigger question to chew on. In a world where we're always short on time and memory, is the perfect answer always the best answer?